Hello and welcome to my channel. As promised, I am doing an English video whenever I get the chance to. You can see that the video is in English by the EN notation on the title. I know that most of you guys know about my channel from my friend Tony from Tony359 channel, so I would like to take this chance to thank him. And today on the bench I have an ATX power supply to repair. This came along with a batch of other supplies, I guess 4 or 5 of them to repair. This one came as it is. It was intended for dismantling, for taking parts from it to fix another power supply which was identical to this one, but it was complete. As it turned out, I didn't need anything from this one, so the owner told me I could try to repair this one as well. The unit is a Corsair CX750, 750 watts. Corsair CX series power supplies feature low noise, cooling, and a compact design for an easy fit in nearly any modern case. Model number RPS 0146. Universal input, universal mains input, meaning it has a PFC, an active PFC converter. It is a single 12 volts rail capable of 62 amps, and it has two step-down regulators to supply the 3.3 and 5 volts outputs, with a maximum combined power of 130 watts, 300 milliamps minus 12 volts, and 3 amps 5 VSB, the standby supply, and a total of 750 watts. Cables and stuff, more specs, downloads, nothing interesting, right? I'll put the link in here in the description part of the video in case you want to visit it. The owner told me that the supply is shorted and they sent this capacitor desoldered, but it doesn't seem to be the one that was in here. It is a smaller diameter, but I do have a new Hitachi 330 microfarads and 450 volts, 105 degrees. I will not use this one because it's only a 400 volts and 85 degrees. Granted, 85 degrees shouldn't really be a problem, but 400 volts is too close to the 390 volts which gives out from the active PFC circuit. What could be shorted on this power supply? I'm not sure, but we are going to find out. Usually the PFC circuit dies out. I'm not sure why. But usually the diode or the MOSFETs blow up. This is the active PFC part. The inductor, the MOSFETs, the diode, the controller IC, and then this is the main converter. These are the two MOSFETs from the main converter. It is a two transistor forward converter. How do I know that? Well, I had a look at it, and this is the clue. These are the catch diodes, each of them connected from the drains of the MOSFET to the power rails. These are the ones here and here. One goes to the negative side of the main filtering cap, and the other one goes to the positive. This is where the cap is. This is a current shunt resistor. Is it damaged? No, it's not. I thought I saw some damage, but it isn't. This should be the MOSFET for the standby power supply. Some EMI filtering. This is the main series inductor for the 12 volts rail. It uses a -52 powder core, iron powder core, denoted by the color light green and blue. Not sure if you can see it. Yes. -52 cores are better because they have about the same permeability as -26 cores, which are yellow and white, but it has way lower core losses, about half if I'm not mistaken. So it helps with efficiency, but they are a bit expensive, more expensive than -26. The bridge rectifier, main bridge rectifier, another current shunt. This should be the current shunt for the PFC section. Fuse is over there. These are the two step-down regulators for the 3.3 and 5 volts outputs, and so on. Let's see what can be shorted. First thing to check is, of course, the fuse, mains fuse, which is over here, and it's blown up, right? Yes, so there is a problem. Let's see the mains bridge rectifier. This is the plus side. So one diode good, second diode good, third diode good, and the last diode good, right? Yes, there is some difference in the forward voltage, but it still looks good, right? We'll leave it at that for the moment. Let's see the current shunt resistors. First, the PFC one. $38 milliohms. Seems alright. And they don't seem damaged. So no problem there. What about this one? This is the current shunt from the main converter to transistor forward. And let's see. 118 milliohms. Seems alright. Should be 120 milliohms, so yes. Now for the power transistors on the PFC side. Drain to source, nothing. And source to drain, a diode drop. Same here. Drain to source, source to drain. Granted, they are in parallel, so if one looks okay, then the both of them are okay. They are definitely not shorted. The PFC diode, this one, seems to be here. Yes. And it is shorted. That explains the fuse blowing up. What about the NPC? It doesn't seem blown up, but let's be sure. No, it is not. It's okay. Let's check the MOSFETs from the 2 transistor forward converter. Should be one here and one here. Again, drain to source, nothing. Source to drain, a diode drop. And the other one, drain to source, nothing. Source to drain, a diode drop. Let's also check the MOSFET for the standby supply. Should be this one. So drain to source, nothing. Source to drain, a diode drop. It's also okay. This small board does the synchronous rectifying part for the single rail 12 volts output. It has several MOSFETs on it. I do not have access to all of them to measure them, but it is easy to check from here to here, because if any of the MOSFETs are shorted out, they are connected drain to source between these pins. And if any of them is shorted, then I should see shorts between here and here. And I don't. This is the output capacitors charging up. But there is no short. So the rectifying part is okay. Which means that most likely both 3.3 and 5 volts regulators are also okay. And I only need to replace the PFC diode. But to do that, I need to take out the whole heatsink with all of these MOSFETs. So let's do it. I will use my desoldering station to take out this heatsink, but before I do that, I will add some leaded solder just to make it easier for my desoldering station. the heatsink is out. When there's a lot of solder involved, I prefer to use my solder pump because it is easier to clean it up. As you have seen, I do prefer resin flux. It is cheap and it does a very good job. These are the MOSFETs from the 2 transistor forward converter, main converter. On editing, I'll put up some info if I can find any. And this one is from the standby supply. 4N7G. Most likely 4 amps and 700 volts. But I will also search for this one as well. This is the damaged part, the diode. 8S2TH061. It is actually an 8S2TH06I, not 1, and it is a 600 volts and 8 amps fast diode. I have this from TME. They are 10 amps, 600 volts, ultra fast diode. Should be slight better than the original. Bigger current capability. I'm not sure why, but most of the power supplies I have repaired had their diode blown up, their PFC diode blown up. I'm not sure why this happens. An 8 amps diode for a 800 watts PFC should be more than enough, but it isn't. I'm not sure why. Maybe the owners do overstress the power supplies, or maybe in time the fan gets clogged up with dust and ventilation is poor. Yes, all the pins are through. There we go. Job done. I want to check the bridge rectifier out of the board, because as you have seen, there seem to be some differences in the voltage drop. So one diode, second diode. Yes, there is some difference. I don't like this. I do have a replacement bridge rectifier. The polarity is switched. The AC inputs are in the middle pins, but the plus and the minus are switched between them, but it is no problem. I can simply switch its position. So let's see the new bridge rectifier. First diode, second diode, third diode, and the last, yes, much more tightly packed. So this one also go to the bin. I will put the text side on the heatsink, and it's just the same. The bridge rectifier is in its place, but before I clean up the flux residue, I need to make sure I did mount it in the right orientation, in the right polarity. This is the minus side because it goes to the current shunt resistor, and this should be the plus side. So, yes. The main filtering cap on the primary side is also soldered on the board. And what comes last is the fuse. I took out the blown fuse, but before I put a new one in its place, I am using this light bulb, a 200 watts light bulb, in its place, because I want to test it to see if I have a working PFC, and this is the safest way to do it. If anything is wrong on the board, the bulb should light up. If it doesn't, then it should be okay. If it is working okay, the bulb should light up for a short moment at the beginning, then it should decrease, it should go out. So let's see. Yes, It did flash for a second, but then it stopped. And let's see, do I have my PFC? I do not, but it could be that the PFC doesn't start until the main converter starts. Let's see if I have my standby voltage. Here and here, there should be 5 volts. Why isn't there on this socket? It is. Maybe I hadn't put the test leads. Okay, so I do have my 5 volts. What comes next? Well, if the power supply does work, when I short the green wire to one of the black ones, I should have 12 volts because I connected my test leads on the 12 volt output on the yellow wires. And let's see. I don't seem to have my 12 volts, but I want to see if I have my working PFC when I start the main power supply, even if for a short period. The voltage drops. Maybe it doesn't like the light bulb. I have temporarily soldered a fuse on the board just in case the power supply, the PFC, does not like that light bulb. And let's see what happens. 330 volts. The fuse didn't blow up. So let's see now. Do I have my 12 volts? No. I am guessing that it didn't like the fact that there was no fan. There was no load on the fan output. So let's see now. I did soldered a fan. So what now? No. I want to see what happens on the high voltage side when I try to power up the main converter. So let's see. Not much. The voltage does drop a bit. I thought I'd check the new diode, the new PFC diode, to see if it's shorted. And look, it's shorted. Or is it? I don't think so because this is the supposedly blown up diode, shorted diode, the original one. And no, not in there. No shorted diode, right? So what else could short out the diode pins to make it look like a shorted diode? One side of the diode, the anode, comes from the bridge rectifier through the inductor, then some jumpers, some wire taps here and here on the drain of the MOSFETs, and then on the diode pins. And the cathode of the diode goes here, and from here through the NTC to the plus of the filter cap. Let's see on the continuity what kind of resistance do I have between the diode pins. Dead short, but no, almost the dead short, right? This is a dead short, almost 100 milliohms, and the diode say 400 milliohms. Where do I have that resistance? I have disconnected this jumper, basically disconnected the diode's anode, the side from the MOSFETs, and let's see if I still have my short. Yes, I do. I have disconnected the other jumper, basically completely isolating the diode from the board. And do I have a short now? What? So the diode is shorted. How? How could the diode be shorted? It is a new diode. I think I have a problem on the board. These are the other ends of the jumpers I disconnected, and I made sure they are not shorted together. And look, there seems to be a short from here to here. But why? I should have an open circuit. I think I know what happened, and it is my fault. I forgot something. I forgot to check the diode which shunts the PFC at startup. It's a diode here, right next to the inductor. If this one is shorted, then it basically shorts the PFC diode. Why did it short it out? I'm not sure, but let's see. This should be the anode side and this should be the cathode. And it is shorted. Not sure how I forgot about this one. I guess it does happen. Despite the fact that you work on power supplies for years. Yes, it is shorted, as I suspected. And let's see, do I have a short now on these jumpers? No, I do not have. Yes. So this was the problem. This was the issue. While having a look on the board to see what the problem is, I have noticed something. This heatsink has a crack here and also here. The MOSFETs seem okay, but I will retouch here, here, and also on the MOSFET pins, just to make sure. Let's put the jumpers back in their place first. The shorted diode is a 1N5406. I have one UF5408. UF stands for ultra fast. Remember this? It is the schematic I have reverse engineered from Tony's power supply, the flex power one, the first one which had the dead PFC. Why am I showing you this? Well, I am trying to explain why the PFC's diode shorted out, the new diode shorted out. This is the diode which straps the PFC at startup, and this one was shorted on this Corsair unit. So, as the PFC tries to start up, it basically increases the voltage at the anode of the PFC's diode, and this end is being kept at the mains level, 320, 330 volts, because this diode is shorted. So as the PFC increases the voltage here, it severely overloads this diode, and that's why it's shorted. As I said, I am not sure how could I forget about this diode. I guess it happens. But anyway, let's get back to work. So I have a new diode on this heatsink, and let's put it back on the board. But before I do that, let's make sure I do not have shorted MOSFETs. Sorry, now the multimeter is visible on the screen, so let's see. Drain to source, nothing. Source to drain, a diode drop. So the PFC MOSFET survived. And these two, yeah, they seem fine. Everything is back in its place now. I did check the mains bridge rectifier to make sure it hasn't been damaged again, and it is okay. I also retouched here, here, and on the PFC's MOSFET pins, just to make sure they are okay. Back with my light bulb instead of the fuse, and no fan. Let's see what happens now. Same as before, but do I have any PFC now? Still no. But what if I try to start up the main converter now? Yes, 377 volts. I am guessing this is the voltage set by the feedback loop on the PFC side. So I do have a working PFC. What about the main 12 volts rail? 12 volts. Yeah. 3.3. Yes. 5 volts main output. 5. Yes. The negative 12 volts. Yes. And the power good signal. Yes. And let's check again the standby voltage. Yes. So all the voltages are there. Let's put a new fuse on the board since everything seems to be okay now. I have temporarily soldered this fan onto the board to make sure I have a working cooling system. And I have here my ATX power supply tester. This LED signifies that the standby supply is working, and when I turn this switch on, the power supply should start, and I should have all my LEDs lit up. So, yes, I have all my LEDs, but this fan didn't start up at all. Is my fan dead? This tester also loads the power supply. It draws about 100 watts totally from it, loading up each supply, each output. So let's see, do I have any voltage here on the fan? No, I don't. I have my ATX power supply tester here, my fan here, and my main socket here, which I'm connecting it right now. I have my standby voltage, and I have my hot air station, my Fenersi hot air station set at 100 degrees C, and this is the NTC, the temperature sensor for the fan. And when I heat it up, at some point, the fan should start. But first, let's start the supply. Yes, I do have my LEDs. So let's heat up the sensor. It doesn't seem to start. It should have started by now. It seems I don't have a working fan. And I want to check something. I have here a PMP transistor in series with the fan. So this is the base, this is the collector, this is the emitter. So base, collector. This doesn't seem right. Even for a Darlington transistor, it should have been less. Is it damaged? This is the transistor 2SB834L. 60 volts and 3 amps. Let's check it outside the board. with the multimeter on view, of course. Base to collector, nothing. Base to emitter, nothing. Collector to emitter, nothing. Emitter to collector, nothing. So this transistor is completely dead. No wonder I do not have my fan. But why? Why did it die? I am guessing someone at some point tried to power more fans from this socket. Maybe higher current fans, and this is a linear control, so maybe the fan couldn't take it and it gave up. This is my replacement PNP, 250 volts, 8 amps. You should know this one. It is from Semi. Let's see if now I have my working fan. I have my green LED. So let's turn the power supply on and see if this thing starts up. Yes, the fan did start up, but I'm guessing it will turn off. Or will it? No, it won't. It keeps spinning but at a very low speed. But let's see what happens if I heat up the sensor. At some point I should have more speed on the fan. I use the connector and these clips to clip my multimeter to the socket and follow the voltage output for the fan as the temperature sensor heats up. And let's see, does it change? Yes. It does take a while, and I had to raise the temperature on my hot air station at 130 degrees until I managed to heat up this entire rectifier board. But as you see, the voltage does increase. So I do have my fan control. And as I said, it is a linear control, which means the PNP wastes a significant amount of heat. And if you put too much load on the fan output, then the transistor will give up, will give out, will get damaged. Sorry for my bad English. Better pronunciation will only come with time. So yes, I do have my working fan. I do have all my outputs. I want to test the outputs again, just to make sure all the voltages are there. So 3.3. It is okay. 5 volts. Okay. Minus 12. Okay. Main 12 volts output. Okay. And the power good signal somewhere here. Yes. Also okay. Standby voltage. Yes. So everything is okay. Yay, victory, right? Before I end the video, I want to discuss something else. I have my second microphone close to the inductor on the main 12 volts rail. Do you hear some whining noise? I hope you can. I'll try to increase the gain on the editing. This is what it's called, coil whine, and it seems to be a common thing on Corsair power supplies. Let me show you. This is Corsair webpage, the help section, and they talk about the same thing. What is coil whine? When current through an inductor changes, the magnetic field around the inductor also changes. This causes a small attraction-repulsion action in the coils of the inductor, which manifests itself as a vibration sound. Power supplies all generate this sound, but often have sound dampening material meant to reduce this noise. This is crap. This is marketing crap. Coil whine has nothing to do with what they claim here, but it has all to do with the way switch mode power supply regulate their voltages. Pulse width modulated power supply, that is, they modify the pulse width in order to regulate the output voltage. Pulse width modulated supplies regulate their voltages by adjusting the pulse width, and the output series inductor does all the work. That coil whine has everything to do with the conduction mode of the inductor, meaning is it in the continuous conduction mode or in discontinuous. I did a theory video of the basic step-down regulator. Granted, it is in my Romanian language, but YouTube should provide adequate captions where I explain basically that the output voltage is the input voltage multiplied by the duty cycle. So, this is only true when the output inductor is in the continuous conduction mode, meaning the current through the inductor never reaches zero. The current through the inductor is a ramp, starting from somewhere and ending at some point. If that lower point reaches zero, then we say that the conduction mode is discontinuous. And if that lower point never reaches zero, then the inductance works in the continuous conduction mode. And the power supply needs this inductor to always be in the continuous conduction mode because when it is in the discontinuous conduction mode, the duty cycle needed to regulate the voltage is very small. Some power supply deal with this by pulse skipping some pulses to maintain regulated voltage while still keeping the voltage feedback loop stable, because this is what happens. It is an It is an instability caused by the discontinuous conduction mode of the inductance, of the series inductance on the output. Why is this happening? Well, from my tests on the other unit like this, I have discovered that this noise is only present at some low output load. After, I don't know what, 150 200 watts, the noise disappears. And this has to do with the current variation in the inductance. Basically, when you calculate this inductor, you have a delta I you need to take into account, and that delta I is what, 25-30% of the total output current. And in this case, with some 62 amps total current, 30% of that is what, 20 amps or less. The output current needs to be at least 10 amps, 15 amps. That is half of the delta I in order to the inductor to work in the continuous conduction mode. And it is difficult. It is difficult at light loads to maintain the continuous conduction mode. So that's why it generates that coil whine. That noise is some kind of instability in the voltage feedback loop, which generates subharmonic frequencies. Those subharmonic frequencies are in the audio band. That's why we can hear them, because the switching frequency is way outside the audio band. You cannot hear them. What can be done? Not much, unfortunately. You can put a minimum load on the board to extract what, 10 amps, 15 amps permanently from the 12 volts. That is not possible. That is not feasible. The other way to treat this whine noise is to work with the voltage feedback compensation network, but it is a very time consuming and difficult job, and it doesn't always work. So, as the video is already very long, I will not even try to work this out. It is a common issue between Corsair power supplies. It is their engineer's job to fix it. And since everything seems to work fine on this power supply now, I am ending this video here. If you watched it until the end, thank you very much. If you liked the video, please give it a thumbs up. And as always, comments down below are always welcomed. If you like my channel and want to support me, you can do so by buying super thanks or by becoming a member of my channel. So, hope to see you soon on my channel. Bye.